We have this differential approximation that says if one variable is a function of another, then the change in output is going to be approximately the slope times the change in input, right? We're just treating the function as though it's linear. In fact, we saw that this is basically the formula that gives you the linearization. Change in y is slope times change in x, right? So we can see how a change in input is going to create a change in the output, at least approximately. As long as we don't make a big change in input, that's going to be true. Now, one place where this happens a lot is if we're doing some kind of experiment. We take some measurement and then we try to calculate something else based on that experiment. We want to know, in any measurement, there's going to be some error in the initial number, right? So there's the possibility that what we got should be changed to be some other value. So there's going to be an error in the measurement, and that's going to lead to an error in the calculation. My calculation is going to be off a little bit. So this is perfect. Trying to figure out the change in the output, then the error in the calculation from the error in the measurement. That would be a great use of differentials. Now, if I tell you that I measured it accurate to within a foot, you need to ask, what did you measure? Because if I measured the length of a pencil accurate to within a foot, you should not be very impressed with my skills. But, if I measured, say, the height of a tall mountain accurate within a foot, you might be more pleased with me. So a lot of times, rather than just talking about the accuracy of the measurement in absolute terms, we ought to talk about the accuracy relative to the actual size. So instead of talking about delta y, that would be the absolute error, you might be more interested in the absolute error compared to the size of the object. So if I measure a pencil and it's accurate within a foot, then the pencil's actually about, well, actually less than a foot, right? I've got this huge error because this number is big in comparison to that. On the other hand, if I measure the height of a mountain, if a mountain's like 10,000 feet tall, and this delta y is just 1, I'm 1 in 10,000, that's a pretty small amount. This is called the relative error because you're measuring the error, the absolute error, delta y, relative to the actual size of the thing. That can sometimes be a nicer comparison. So here's an example. We're asked, how accurately must you measure the diameter of a sphere in order to calculate its volume to within 1%? So we want, we see this 1%, that's 1 in 100, right? That's some kind of fraction, some comparison. So we're talking about relative error in this case. Okay, so we're going to make some measurement. We're going to plug it into a formula and calculate its volume. And we want to ask this question about the error. Well, first we got to ask ourselves, what formula do we use? How do you get the diameter of how do you get the volume of a sphere from the diameter? Now, you might remember that the volume of a sphere is 4/3 pi r cubed. But then we don't have the radius, right? But the radius is half of the diameter. So if I replace this with d over 2, then I get 4 times pi times d cubed all over 3 times 8, right? So the 4 goes in there twice, and we have this formula that the volume is equal to pi d cubed over 6. Okay, so there's the volume from the diameter. The question is, I'm going to measure this diameter, and I want to know how accurate will my volume measurement be. Well, we know that the change in v is going to be approximately equal to the slope, which if you take the derivative here, the 3 comes down, you get pi, you get d to 1 power less divided by 6 times the change in d, right? That's the thing that we were measuring, was the diameter. Okay, so change in output is slope times change in input. I can simplify this a little bit because the 3 goes into the 6 twice. So we have change in v is approximately pi d squared over 2 delta d. But we're talking about relative error, right? So we want to find not just the error in the volume, but the error compared to the actual volume. So I'm going to divide both sides of this equation by the volume. Of course, we know how we're getting the volume from D. We're calculating, what did we get? Pi d cubed over 6, right? Cubed over 6. If I just simplify a little bit, I can see that this d squared on top will eliminate all but one of those d's down below. Pi is in the top and bottom, so it will go away. I have this fraction, tiny fraction with 2 in the denominator. Here's another one with 6 in the denominator. If I multiply top and bottom by 6, those tiny denominators go away, and I find that the relative error in the volume is approximately equal to, let's see, 6 divided by 2 is 3, so I get 3 delta d, and the 6's here cancel, and there's just 1 d left over. So it's 3 times the relative error in the original measurement. So if I want the relative error in the calculation to be 1% or less, let's just look at the worst case scenario, then that tells me that the relative error in my diameter measurement has got to be about 0.01 divided by 3, so 1/3 of a percent, in other words. Let's look at this again, but let's do it with surface area. So erase what was over here, and we'll do the surface area. Let's see, the surface area of a sphere, I know it in terms of the radius is 4 pi r squared, but again, we're talking about the diameter, and the radius is the diameter over 2. So we end up with the formula being, let's see, 4 times pi times d squared over 2 squared. That's just going to be pi d squared is the formula for surface area. From the differential approximation, the change in the output of our calculation is going to be the slope, which is 2 pi d times the change in our input, at least approximately. So now if we're interested in the relative error, though, we want to take those absolute errors and divide them by the actual amount of the thing that we're calculating. So we have the error in S, error in surface area, over the actual surface area. Now we know that we can calculate the surface area from pi d squared. So we have 2 pi d delta d all over pi d squared. And notice that the pi's cancel. This d will take out one of those d. So we have that the relative error in S is twice the relative error in D. So if you want the relative error in S to turn out to be 1%, right, then the relative error in D needs to be half of that. So that would be 0.05, or half of a percent. Here's an application where we can use a differential to calculate the answer quickly. We've got a tennis ball. Its outside diameter is 6.7 centimeters, and there's about 2 millimeters of material on the outside. So we want to find how much material. If you think about a tennis ball, it's the outside is a sphere, and then there's a hollow sphere on the inside. So if we want to find the amount of material, we could find the volume of the outside and subtract the volume of the inside. But knowing the formula for calculating a volume, since the volume is pi d cubed over 6, then we could just ask if we make the diameter shorter. So, and since the material is about 2 millimeters thick, so that will be on either side, right? So if we make that diameter shorter, then we would have a change in the volume. So we're going to change the diameter. We're going to change the diameter by 4 millimeters, and we want to know how much does the volume change. We could calculate the exact answer by finding both volumes and then finding the actual difference in the volume. But we also know that the difference in the volume is going to be the derivative, which is pi d squared over 2 times the change in diameter. Now, pi d squared over 2, let's see, the diameter of the outside we know is 6.7, so we can take 6.7 squared over 2 times the change in the diameter. Now this is in millimeters. Since we're doing this in centimeters, we better convert everything into centimeters. If we do that, then the answer will be in centimeters cubed. If we did everything in millimeters, the answer would be in millimeters cubed. But we started with centimeters here, so I'll put in a centimeter is a tenth, or a millimeter is a tenth of a centimeter. So we're changing it by 2 millimeters on this side and 2 millimeters on that side, which makes a total difference of 0.4 centimeters. Of course, that goes in there twice. So we find that the approximate volume of material for this is going to be pi times 6.7 squared is 44.89 times, we've got times 0.2. So if I calculate that, I think we get about, see, using pi here, we get about 28.2 205 there as the volume. Now, the other thing that we can do is to actually find the difference between these two. This is kind of the slower way to calculate the exact value. We know that the real change in volume is the volume of the outside sphere, which has diameter 6.7, so we'll take pi diameter cubed over 6 minus the volume of the inside sphere. This one is let's see, cubed all over 6. So the inside one is 6.3 because we had 2 millimeters on each side. Let's find what that value actually is. So when I plug that in, I get the actual change in volume is 26.555. So we got it to within about, what have we got, about within 1.5 centimeters cubed. But we were able to avoid as much computation by using the differential. So we get a reasonably good answer for the volume of the material just by using the linearization of the function.